This is notes 9.3 about slope fields. So we are going to be talking about slope fields, how to get a solution curve from a slope field, how to get a slope field from a differential equation, and how they're all interconnected. So we are going to start off with a mini lab. Step one, go ahead and solve that differential equation. Remember, first step of differential equations is to get your prime notation into Leibniz notation. We have it. What is step two? Step two would be to separate your variables. When we have multiple terms, if they don't have another variable with them, assume that it is the variable that it's with. So I see a +2, I'm going to assume that that is going to stick with my x. So we're going to treat that entire right side as a factor. So with that being said, go ahead and solve for your dy and your y variables on the left side, get your x variables on the right side. So here's what we should get. So technically there's a 1 in front of my dy, and now we are ready to integrate. So go ahead and find your antiderivative. On the left side, the antiderivative of y, or of 1 is y. On the right side, antiderivative would be 1/2 x squared plus 2x. Keep it general, there should be a plus c. Remember, you're going to keep it general on this side with your independent variable. That is our solution for our differential equation. In step two, I have various initial conditions for you. So I'm going to do the first one with you, and then I'm going to give you time to do the rest. Let's see, I have space at the bottom. So for our first initial condition, y of 0 equals -3. So 0 would be my x value. I'm going to replace all my x's with 0. And then my output is -3. So obviously, if I solve for c, most of my terms on the right side are 0. I'm left with c equals -3. I'm going to go ahead and write my particular solution with a c value of -3 for my first initial condition. All right, go ahead and do the rest of those initial condition problems and write the particular solution for each. The correct answer will appear in 3, 2, 1. And there we have it. So now we are going to plot these 5 particular solutions on our graph. What I'm going to do is type each of them into our graphing calculator. So I'm just going to do the first one right now. All right, so that's 1/2 x squared plus 2x minus 3. And then I'm going to go to my table. And I have my calculator set up so that I can enter my own x values in. If you would like to do that, remember to do that. It's second window. And then you make it so that you are asking your independent variables or really entering them in. Okay, so on my graph, yep, I have x values that go from -6 to 5. So I'm going to see if I actually have an output that is within my actual grid here at -6. If not, I'm going to start finding my first outputs that actually appear. So let's see, -6, output of 3. So we can plot that. -5, -0.5. I am only going to plot whole number outputs for now unless I have very few outputs. -4 is -3. -2 is -5. Ooh, okay, so I am seeing that I'm getting the same output as I did for -3, and -3 and -1 are both the same distance away from -2. So that tells me that -2, -5 is my vertex. Don't believe me? Let's take a look at the graph. Which doesn't go all the way down. We'll do zoom 6. Yeah, that's definitely -2, -5. So I can go ahead and start reflecting my outputs over the axis of symmetry. That is not right. So my axis of symmetry is -2. Hold on. Axis of symmetry. There we go. I'm going to get rid of all my little dots there. And we can go ahead and plot that curve. All right, I want you to go ahead and plot the other 4 functions, and mine will come up in 3, 2, 1. So hopefully you notice that all of these particular solutions are just vertical shifts of one another. All right, so what I'd like to do now is talk about a new concept, a slope field. So step 3 says evaluate the derivative from step 1. So we had our differential equation, which is a derivative. From step 1, dy dx equals x plus 2. So remember, what does a derivative represent? Slope of the tangent line. So derivatives, oh, I was using the eraser, are slopes. So we are going to be drawing little tiny slopes at every single coordinate. So our differential is solved for dy dx. That's an important thing here. Dy dx is isolated. So in order to figure out the slope at every single point, I'm going to plug my x and y values into my differential equation. Now, I don't have any y values in there, so all of my slopes are going to be dependent on x. If I had x plus y, I'd be plugging in both values, but I just have x's in here. So for -4, 2, I'm going to take my x value of -4, plug it in. -4 plus 2 is still going to be -2. So technically, for this entire column, since I have the same x value and the derivative doesn't depend on my y value, these are all going to be -2. Go ahead and fill out the rest of the table. Remember, you only need the x value for this specific derivative to figure out the slope at every single point. I'm going to put mine up here in just a moment. Here we go. Okay, so now we are going to draw our first slope field. So what that looks like is if you, let me see if I have one in here. If you flip to the next page, that is what a slope field looks like. So at every single coordinate, we are going to draw a tiny little line with the value of the slope roughly drawn there. There are some slopes that you always want to start off with. You always want to start off with your slopes of 0 and 1. Reason being, 0, very easy to plot. A slope of 1, that is what you will gauge all of your other slopes relative to. So if I happen to have like a slope of 1/2, I know that if I draw a slope of 1, a slope of 1/2 is going to be half as steep. If I have a slope of 1 plotted, my slope of 2 will be doubly as steep. So you always want to start with 0s and 1s, and technically -1s as well. So let's see. My slopes of 0 are going to be all of my -2 x value coordinates. And is a slope of 0 a vertical or horizontal line? Hopefully we said horizontal, because remember, every time we have a horizontal tangent line, you say that the slope is 0. So if I happen to have a vertical slope in my slope field, what would that slope have been from? Hopefully you said division by 0. So that would be like if I had an x divided by y and I had y values of 0, I'd draw a vertical line there. Because we can't have like vertical lines in our slope field. That would just be where a vertical asymptote ends up being here. Okay, so my slopes of 1 are the -1s for my x values. So what I like to do for my slopes of 1 is draw a tiny little line that is about 45 degrees. Do not make these very long at all. You do not want these to go too close to other points. Try to be very consistent. You notice that you're being inconsistent, like I am down here. Ugh. So much easier on paper. You want to erase. Now I'm going to draw my slopes of -1, so I have roughly that same type of slope, but in the negative direction. Okay. For slopes of 2 and -2, make it a little bit steeper. Because we still have a slope of 3 to draw. I don't want to get too crazy. So I'm just going to draw something slightly steeper than that. Make sure that whatever you draw here is just as steep as your 2s, but in the negative direction. And then for my slope of 3, I'm just going to make that even steeper. I don't have anything else that I'm going to draw steepness wise. So there we go. That is our slope field. Now, what I want you guys to look at is how does this compare to our particular solutions back in step, what was that? 2. So go look back at your particular solutions from step 2. How do they look compared to this? Hopefully you're seeing that it's a similar shape. These slope fields are taking on a similar shape to any graph. So what a slope field will help you do is, let's see, one of the particular solutions was, I think, 0. Let's do 0, -1. So if I were to plot that particular solution here, I would use the slopes around it to go ahead and try to sketch that particular solution. So I see that it's going down, and then roughly when I get in this area, it's less steep. And then over here, it flattens out. Okay, and then over here, it gets a little bit steeper. Oh, and then a lot more steeper. And then over here, it's gonna keep going. It's, oh, very steep, very steep. So if we look back at our graph for the slope of -1, keep in mind this grid is a lot smaller. Let's see, I went down to -2, -3. Is that what I did here? I didn't quite make it that far down, but roughly I have the shape that I'd want for that graph. So keep in mind, I am roughly drawing this based on my slope field. And I guess I noticed I didn't go quite as far down when I was in that section as I probably should have. So I'm going to erase all that. And I want you to go ahead and answer question 1. What does the derivative at a point represent? Okay. So what does the derivative at a point represent? You answered this already. The slope of the tangent line at a point. So that is what we drew in the slope field. Question 2, describe the relationship/connections between the differential equation, the slope field from step 4, and the particular solutions. So just any relationships, whether it's just like pairwise, you're describing how you would get one from the other and vice versa. So I'll give you a moment to submit any sort of ideas for that. Right. I'm going to type some of the things that I came up with. You might have come up with more connections. These are just a few that I have. So one connection, let me see. Here we go. Is that you can draw a particular solution graph from the slope field. And maybe I shouldn't say draw, maybe I should say sketch, because it's not perfect if you're doing it by hand. Now, if you're using technology, it'll do it perfectly. And then the other thing that I have is that you can use the differential equation to plot the slope field by evaluating it at certain points. So just kind of summarizing what we did here, really. So if you need to pause that to write any of those things down, if that's not something that you observed, go ahead and do that with the video, please. All right. So slope fields, what are they? A slope field is the graphical representation of particular solutions to a differential equation. We already talked about that. How are they created / drawn? Again, already talked about it, but I'll read this. You first calculate the slopes at several points in the coordinate grid by plugging the xy value into the differential equation. Make sure, again, that dy dx is isolated. Then you plot the slopes as short line segments at those points. Keyword being short, you do not want to draw these too long, otherwise you will start having the wrong slopes in wrong areas, just because you might be infringing on some of the other coordinates nearby. How or why do we use them? You can use them to plot particular solutions for a differential equation. We do this by starting at the coordinate of your initial condition, and then you use the slope line segments as guides for how you are going. You are not necessarily connecting those slopes, you are just using them to help you draw the slope in that area. Is there practical use for slope fields? Absolutely. One use for a particular slope field model is the predator-prey interactions. You can use that to predict the growth rate of prey based on the levels that are varying in the predator population. So like if you have an initial condition for your predator and prey, you can predict how the predator and prey will change depending on like time. Okay, so for example 1, I want you to sketch the particular solution through the point 1, 1, and I'm going to add to the instructions here. I also want you to do it through 0, 2. Wait, do we want to do 0, 2? No, do 2, 0. All right, so do both of those, please. I will put mine up in a moment. I'm going to have you pause the video to do that for yourself. All right, so 1, 1. That's here. So roughly, I'm going to be starting at like a 45-degree angle. Oh, I'm going to get a little bit steeper. All right, in this section, about a 45. Oop, in this section, it's going to be flat. Okay, now we're going down 45. Oop, even steeper. Even steeper. There we go. All right, 2, 0. It's here. Super steep. Super steep. Less steep. Oop, in this section, we're going to flatten out. This section, going a little bit steep and down. Yours does not need to look exactly like mine, but it should look similar. But what I would like you to do now is decide which of the following functions that slope field could represent. Now, keep in mind, you also have 2 particular solutions graphed. These functions might not necessarily be the particular solutions that we've graphed, but imagine if they could be graphed on this function or on that slope field or as a result of the slope field. Okay, so ones that I'm going to eliminate, those are definitely not linear functions. They're not quadratic. In fact, I think they look more like cubic. 1 over x squared, that looks like this. And I don't see any vertical asymptotes on that y-axis, so definitely not going to be this. So definitely not going to be this. Oops. Cosine would have a more periodic look to it, and it doesn't look like I'm going to keep having that periodic pattern. Same thing with sine. Ln absolute value of x. Ln looks like that, so it would actually be like that on both sides. Not what I have here. 1 over x, just like with the 1 over x squared, there's going to be that vertical asymptote on the y-axis, not happening. If I had a constant function, this would just be representing a bunch of constant functions. So I would have horizontal slopes everywhere. And that's not what I see here. So what I discussed earlier, definitely have a cubic. And what we see up top is variations of a cubic function being plotted in the slope field. All right, last example, which of the following equations is this the slope field of? So what you could do is you could go ahead and try to plot a particular solution, solve each of these differential equations. However, that second differential equation is going to make it very difficult because we have subtraction between the two variables. And what we want is multiplication and division between the two variables. So we have to change our strategy here. So my suggestion is think about how slope fields are created from the derivatives. What do we do? Plug certain coordinates into the derivative, see if you get them. So what I like to suggest is pick a few different key slopes. Slope of 0, slope of 1, slope of -1. So some coordinates that I see with those particular slopes, not slopes, -1, 1. This looks like it has a slope of -1. Not quite sure, but at least I know it's, I'm sorry, +1. 0, 1 looks like a 0 slope. And then 1, 1 looks like I have a slope of -1. Could be something else that's negative, but at least I know it would be negative. So I'm going to kind of make a table out of these. And I'm going to plug those coordinates into my derivatives. So I'll do the first column, 1/2 times an x value of 1 plus 1. That gets me a slope of 1.5. Let's see, at -1, 1, I have a positive slope. Like I said before, I don't know if it's an actual slope of 1, so I'm going to go with that. 1/2 times 0 plus 1, I'm getting 1. At that coordinate, I wanted a slope of 0, so that tells me that this is automatically out. I want you to go ahead and continue the table. I will put the values that I'm getting for everything down, even if I didn't actually need to go through it. So like for the last one here, I did end up getting 1.5. And even though I wanted a negative, so there's kind of two things going against that. Go ahead and finish. My answers will be up in 3, 2, 1. So hopefully you got the same thing as me, that the last derivative or the last differential equation is giving us the slopes that we want in that area. At the bottom of the notes, we have a summary between the relationship of everything. You can give that a read. I'm not going to read it to you. And that is the end of the set of notes.